Hello, and welcome to today's session of Working Efficiently with Oracle. In today's session, we are going to be talking about the memory architecture of Oracle databases. This is the second in the three series which talks about Oracle architecture. Here's the series objective. What are we covering today? In today's session, we're going to be talking about the various components that comprise of the memory architecture of the Oracle database. By components, we mean the areas within the server where the Oracle instance is running that are allocated to specific functions. So we'll try to cover as much as possible with regard to the memory structures in today's session. We also will cover uh, a little bit about memory management. Just as a recap, the Oracle instance is a collection of memory structures and background processes, and it is only through the instance that you can access the data within your database. So the Oracle instance runs on your database server, and unless it is started, you will not be able to access information from your database. So going to the main topic of today's session, which is the memory components. When we mean memory components, this is nothing but set of areas allocated within the memory which are used for specialized functions. If we look at the Oracle memory architecture, predominantly you will see that there are two components. The system global area, which is also referred to as the SGA, and the program global area, which is referred to as the PGA. Just to give you an overview of what system global area is, we also used to call it as the shared global area. The reason being, all the components of the SGA are accessible across sessions which are actually using the database. So information that is there in the SGA can be used by more than one session. On the other hand, program global area is also called as the process global area, and the process global area typically is associated with the background process and the server processes which are running on the database server. So moving to the system global area. So what is the purpose of having the system global area? When we talk about the memory components, there are a lot of sessions which access the Oracle database, and each session does its own set of activities. Now, if we were to assume that every session would have its own individual memory and that it would not share information across sessions, then there would be a lot of resources that are consumed. Apart from that, there are a lot of benefits that can be accomplished by sharing this information. So, when we talk about system global area, it is a shared component of the Oracle memory which is accessible by all the sessions. When we mean sessions, we are talking about server processes, which are programs which run on behalf of the database server, servicing the requests of a user process, which is nothing but a program that is written by the client or the program that interacts on behalf of the client. So, if we have to look at the system global area components, we have some major components and we have some minor components. So, the major components are the database buffer cache, the redo log buffers, and the shared pool. There are certain other components such as the Java pool, the streams pool, and others which will also be covered later in the session. Moving on to the database buffer cache. Now, the database buffer cache is that part of the server memory, the main memory or the RAM as it is called, where you are loading information from your database and storing it for further processing. So, Oracle allows you to create table spaces which are nothing but comprising of physical data files with different block sizes. So there would be a default block size that you create when you create the database, and then going forward there would also be provisions where you can create different block sized table spaces. So if you have, let's say the default database size, block size is about 2K, then you should be having the memory also in chunks of 2K, so that there is no mismatch between the memory size and the database block size. So typically it's a good idea to have the block size as a multiple of 2. Now, in case you have a requirement where part of your job is running batch programs, which does a lot of select and lot of manipulation, in that case, it probably makes sense to have a larger block size. So, to handle such capabilities, Oracle provides you with the ability to create different table spaces with different block sizes. So, in order to facilitate that, it is essential that you also allocate memory which correspond to those different block sizes. So if this is the major chunk which is actually being used by the default block size, and you don't have too many table spaces with different block sizes, then accordingly you can adjust and configure your Oracle memory. So here we can see that, let's say the default block size is single K. Then you can see that we are getting different blocks created for 2K, probably 4K, 8K, and probably NK as well. So this all this is configurable, and this is something that you can do at your databases. So please keep in mind that your block size, your cache size has to be typically a multiple of whatever your database block size is. Now, all this information, all these memory structures, or rather all these database buffers, are typically used to store data. So this is simply, it just gets the data from the data file on the disk and stores it in the memory, and only after this you start seeing it in through your application. Now apart from this, there are buffer pools also available within the database buffer cache. Now buffer pools offer a slightly specialized function. Before I go to the specialized function, let me also talk to you quickly about the least recently used algorithm. This is the algorithm using which Oracle manages its buffer cache. So typically what happens is, this algorithm is nothing but it maintains a list of the block addresses. And typically what happens is, when there is data which is coming into the buffer from the disk, it is actually placed at the most recently used end of the LRU list. So the LRU list has two ends. One is the most recently used end and the other one is the least recently used end. Now as more and more blocks start coming into the memory from the disk, and this particular blocks that we earlier retrieved are not being used, these blocks are slowly pushed towards the LRU end. Now with every request which is being serviced by these blocks will go more towards the MRU end, but otherwise they will be moving toward the LRU end. Now once they reach the end of the LRU list, if there is no request for these particular blocks, and at the same time there is a request to get more blocks into the list, then these buffers are returned back to the disk. So that is how the LRU algorithm works, and that's how the blocks uh, actually operate within the memory. Now, sometimes you may know that certain information needs to be available all the time, and you cannot afford to have it swapped between the disk and the memory. So, in such scenarios, you can leverage the buffer pool feature. So, there are two types of buffer pools. One is the keep buffer pool, the other one is the recycle buffer pool. So in keep buffer pool, you're basically telling Oracle that, hey, I know that I'm going to be needing this information, so keep it in memory for a longer time. And in the recycle buffer pool, you're clearly telling Oracle that whatever I'm doing right now, it's more transactional, and after the transaction I may or may not need this data, so I'm not worried about it. So this is how a database buffer cache looks like. Again, as I said, this is for a conceptual understanding of how the database buffer cache functions. Now, within the database buffer cache, the database buffer has multiple states. When initially the instance is started up, the blocks are empty. It is also referred to as an unused state. This means that this block is ready to be used, and there are absolutely no weights or no resources locking it at this point of time. Now, when this particular action happens, I mean, this block is being used because somebody has requested to do an operation. It could be a query or it could be a data manipulation operation. So when the request is being executed, let's say in this case, a person is wanting to execute a query. When this request is executed, the data is fetched from the data files and is loaded into the memory in the database buffer cache. Now, if this data is not modified, okay, and at the same time, if this data is also slowly moving towards the LRU end because it's not being used later, it continues to be clean. It's called a clean state. And what happens here is, if some other data request is going to come in and there is no space in the memory buffer cache, then Oracle would reuse the same buffer cache for getting fresh information. On the other hand, if this data is modified, it is referred to as a dirty buffer. And if a data is modified, it is uh, called a dirty buffer. And this means that this particular buffer is being marked for being returned to the disk. So the changed data has to be returned to the disk before new data can again come in. The next slide talks about the buffer modes, or rather the access modes in which you can pull data from the buffer. Now, a current get is also referred to as a DB block get. Now, if the data is being fetched uh, and the data has not changed since it has been fetched into the memory, it is referred to as a current get or a DB block get. Now, typically when a particular session makes a change to a data in a buffer, the data block actually contains a new information. If the same session is requesting this information which is not committed yet, it is referred to as a current get or a DB block get. Now, if this information is requested by a different session altogether, Oracle cannot show the uncommitted data or uncommitted version of the data. So, in such scenarios, Oracle will use the undo information and it will create a read consistent view of the uh, block. So, in such scenarios, that is referred to as a consistent get. When Oracle reconstructs the block contents based on undo information, it is referred to as a consistent get. If Oracle doesn't have to do that, it is referred to as a current get. The next component of the SGA is a redo log buffer. So what exactly is a redo log buffer? Every minute change that you do to the database, everything is recorded and is stored as a redo record in the redo log buffer. Now, if we have to dissect a redo record, it is a collection of change vectors. And a change vector is simply any atomic change that happens to a database. Now, just to illustrate this, let's take the example of an update statement. When a user updates a specific row in the table, there are three changes that happen. The first change is that the data in that particular block is changing from an old value to the new value. Now, this is the first change vector. The second change vector is created because the old information is being stored in the undo segment. So, in the event of a rollback, Oracle would get the data back from the undo segment and apply it back to the block. Now, there is also a third change vector that is generated because the undo segment is maintaining a list of transactions in itself in a place called the transaction table. So there are three changes that are happening here. So and each change is associated with a change vector. So you have the original data being modified, the undo data being generated, and a change to the transaction table. So these three change vectors together comprise a redo record. So typically what happens is that there is a there is the server process would initiate all the redo records to be stored in the redo log buffer. Now please note that this is generated at a very high pace. When we talk about redo log buffer, it comprises of the changes. And how does this writing mechanism work? Because redo log buffers are not huge like database buffers in the memory. So when we look at how Oracle uses the redo buffers, they are more like used in a circular fashion. So changes are being written to the redo log buffer, and as you can see, the changes go back, and finally what happens is once the buffer is filled up, changes are going to be overwritten again from the beginning of the buffer. Now please note that there is a background process called as a log writer, which takes the information from the redo log buffer and stores it in the log file. Now that is how the changes that are being made to the database are moved from the memory to the disk. So since this is a circular buffer and there's a lot of information that's happening, the log writer process does not wait for a long time to start writing the changes. So there are certain criteria based on which the log writer initiates writing the redo records to the log file, and this is something that we will cover in the uh, third part of this architecture session. Next, this is not exactly within the scope of this, but since it is related to log writer, we spoke about the redo log buffer, we spoke about the log buffer writing mechanism. We also will just cover the log file writing mechanism. Now, when it comes to the Oracle database, there will always be two groups at a minimum. So you cannot create a database with one log group. Now, every group can have multiple members, and each member is a mirror of the other member within the group. So when Oracle uses log writer, the log writer starts writing to one of the groups. So please understand that at any point of time, only one group is active. Now, as soon as it finishes writing to the group, it moves on to the second group. And after it finishes writing to the second group, it gets back to the first group all over again. Now, in case you have a business requirement to restore the database till the point of crash, then this is where you put your database in the archive log mode. And then there is another background process called as the archiver, which actually makes a copy of your log files. The files which are archived are referred to as the archived log files. Those are things that we look at a later session. Now, the next important component after the database buffer cache and the log buffer cache is the shared pool area. Now, this is very important both for a DBA as well as for a developer. Now, the shared pool area comprises of the library cache, the dictionary cache, and the result cache. Now, within the library cache, there are two components. The first one is the shared SQL area. Now, what exactly is stored in the shared SQL area? Now, we will not go in depth at this particular point in time, but please note that whenever you execute a select statement, the select statement first has to be passed by the Oracle software, then it has to be executed, and it has to be, once it is executed, the rows are fetched from the either from the buffers or from the data files. Now, shared SQL area stores all the pass statements with the corresponding execution plans. Now, please note that an execution plan is the set of steps that Oracle is using to fetch the data from the database. So, if you can see, the shared SQL area consists of parse SQL statements, it consists of SQL execution plans, and finally, parsed and compiled PL SQL program units. Now, parsing from a performance perspective is a very expensive affair. So, the strongest recommendation always is to minimize the number of parses. So, that will be a topic that we'll discuss, in a later session. Now, this is what is present in the library cache. Now, there's also a component called as the private SQL area. Private SQL area typically is a part of the program global area, which is something that we'll be seeing later. But in the case of a multi-thread architecture or a shared server component uh, architecture, in such scenarios, the private SQL area is also part of the shared pool area. The next component is the dictionary cache. Now, as you know, Oracle uses a data dictionary, which is uh, data about data. So, to do any activity, Oracle always has to refer to information from the data dictionary. So, this particular part of the memory is dedicated to store information from the data dictionary. Starting Oracle 11G, you have something called as a server result cache. So, a server result cache stores information which has been collected from the execution of a query or from the execution of a PL SQL program unit, a procedure, a function, a package, anything. Now, once the data is cached in the memory, it becomes faster for subsequent references. So that is the advantage of having the server result cache. The other components which are there within the memory, they include the large pool, the Java pool, the streams pool, and the fixed SGA. Now, the large pool is a component which is configured typically when you are using either Oracle XA or you need to have RMAN that is configured, and RMAN needs to use chunks of memory for its operations. In case you're writing a lot of Java code which is stored within the database, then you would need to configure the Java pool. So here we're talking about embedded Java code within the Oracle database. Similarly, if you're using streams to replicate data between databases, in that case you would have to configure the streams pool. Now the last component is the fixed SGA. It is a part of the memory that is allocated and stored for Oracle's internal activities. I mean, Oracle typically doesn't talk about what is there in this, but we are assuming that it is a software code which is being stored in the fixed SGA. And the size of the fixed SGA differs from version to version. Moving on to the program global area. The program global area is a part of memory that is associated with the server process, the background process, anything that is happening on the database server. This actually looks at the process operation, and in case it has to, in case the process drops or the connection drops, then it is the responsibility of certain all that information is typically stored here in the program global area. So when you talk about this stores information specific to process, private to a process, okay, and this is not shared with other sessions. Now in case you are using a shared server architecture or multi-threaded architecture, then the PGA is also part of the main memory. It is not associated with only one server process. Now, if you have to look at the components, you have the SQL work areas and the private SQL area. Now, SQL work areas are specialized memory chunks for specific activity. So, for example, you connect to the database, there is a PGA which is allocated for your specific session. And within that, based on the configuration, you have a sort area allocated. Sort area, as the name suggests, is the memory that is used for sorting your data. So it would be a good idea if you know how your sort area is sized so that your queries perform accordingly. You also have a hash area. Now, hash area is typically used when you're trying to join data from two tables, two or more tables, and there is a hashing join that is involved. Same thing with respect to a bitmap merge area. So these are all specialized areas for specific activities, as I mentioned earlier. Apart from this, there is the session memory. So any of the parameters that you have set specific to a session, those would be stored in the session memory. And those would also definitely have an influence on the way your database is performing or your application is performing. Then you have the private SQL area. Typically, the private SQL area is part of the PGA, but in the shared server architecture, it is part of the shared pool. So within the private SQL area, you have the persistent area and you have the runtime area. Now, persistent area contains information about your bind variables if you're using them. What are the bind variables? What are the associated values? It also has a copy of your past SQL statement, and it is persistent and it is maintained till uh, your session is active. On the other hand, the runtime area is that component of your private SQL area which is used when and it captures information about the SQLs that have been executed, and it shows information such as like how many rows have been fetched so far, what is the state of this, I mean is the cursor still open, information like that is typically stored in the runtime area. The last section of this session is about memory management. Now, as you saw, Oracle has a lot of memory components, each performing a different function. So it could be a nightmare to manage all of these components unless and until you know exactly what you are working with. So, in order to make life easier, Oracle came up with the concept of memory management. So, there are three types that are available. One is at an overall memory level where you just have to specify one or two parameters and Oracle handles sizing of the various components based on usage. The second is automatic shared memory management. In this scenario, you are just setting the SGA to be automatically managed by Oracle and you are having control on how the PGA components are configured. Third is a manual memory management where every component of the Oracle memory is being managed and controlled by your values. So unless you really know how your database is performing, what are the typical loads, what is the quantum of data that is being modified, it is always advisable to take the help of either the automatic shared memory management or the automatic memory management. So with that, we come to the end of this particular session on the memory components of the Oracle architecture. We hope you found this session informative and useful. you need any clarifications, please do not hesitate to contact us at the email ID given. Thank you and happy learning.